Everyone is hungry. So good afternoon. So before we start, let's make this presentation more interactive. So as you can see that I am talking about the pharma application. So how many of you are involved or directly working on pharma applications? Anyone? So one sir is there. So he will be the main information provider to me in this presentation. And as a performance nobody is there, so that means whatever I say it is right. Right. Okay. So to begin with, there are some slides which you can see there are common between me, Dr. Rashid and Sudhir. So I'll just keep it. So this is a slide which is talking about what is the Orbitrap product folio we have. We have Orbitrap in LC also, we have Orbitrap in GC also. And this is the GC Orbitrap models where you can see GC Orbitrap Exploris and GC Exploris 240. These are the two models available. And these are the specifications of these two models, depending on the resolution and ideal detection you can differentiate. And these are the different applications which can do. Like for simple application, you can go with the lower 30K or 60K resolution, but for a specific applications where the structural elucidation or maybe when we talk about the very complex sample matrix, 240 will be the right portion for. Now when it comes to GC copy, as everybody has mentioned, there will be a simple workflow. Just shoot your sample, take data in full stack, and then you process it. And you can get all information about your sample. Whatever compounds are ionized and detected by your system, you can just get it, the information like what you are expected, you can get it by just extracting those masses. What is suspected, you are not targeting, but you wanted to know whether these compounds are present in my sample or not. That we can also do. And the third part is completely unexpected. That means nobody knows, but I wanted to know what are other compounds may be formed in my sample and which I can identify those things. Where we can apply this concept for everywhere like expected, when we talk about, Dr. Dashit already mentioned about the pesticide, where we are targeting about 200, 400 pesticides in sample matrix. Then environmental contaminants or some doping or forensic toxicology, where we can go for the suspected. Unexpected means we don't know, like it may form in sample instability, like the extractable leachable or the pharma impurity, identification and characterization. Now, when it comes to pharma, people are doing lots of this, like purity analysis, impurity analysis. So whether we can propose this GC-HRMS for all this analysis? The answer is no. We can go only for a specific application which can be done on GC-HRMS. Like there are two issues. If you see last couple of years, can I answer if I forgot something? People are talking about the nitrosamine impurities. That is the one major concern comes in pharma, because if you see the history of nitrosamine impurities, it started somewhere around June 2018 when the first NDMA, N-nitrosodimethylamine, was reported in one certain API. And from that, the whole pharma industry had started looking for different solutions. Health Canada is the first one who introduced a method which is based on the GC-HRMS, where they are targeting NDMA and NDEA. But later on, slowly, this nitrosamine impurities start increasing, and now we are targeting about 7 to 8 impurities in various APIs like valsartan, the sartan groups are there, then we have metformin, then we have ranitidine. All those, wherever people are doing, there is a possibility to form nitrosamine, they are targeting. And nowadays, if you have seen, the people are also targeting the raw material which are used in formulation, because the limits are too low. Like for general identification, you can use one single cord, triple cord, but when the limits are less than 30, 50 B, you require at least a more sophisticated instrument, and where this HRMS plays a crucial role. So first we talk about the targeted analysis, where you can see these are the major analytical challenges people are finding in the nitrosamine analysis. One is the selectivity. When you talk about API, it is very good. You are just taking API and you are extracting and you are monitoring this agrometer. But when you convert into finished good, when you are converting this API into a tablet, you will be using lots of excipients or different additives are added, and they may also contribute in your sample extraction and makes your sample more complex, and with the help of more resolution power you can able to analyze those things. Then there are some chemical interference like Sunil has already mentioned, DMF and NDMF. Both are having a almost similar mass, 74. Then you place a major issue. Sensitivity is becoming a more challenge, because earlier it was somewhere around high ppb, now people are talking about less than 30 ppb for all the impurities. And regulatory compliance day by day, like as I mentioned, the health canal is the one, then USFDA has introduced 4 methods, and now you can see there are general chapters published in all pharmaceuticals, USP as well as EP, which are targeting nitrosamine impurities at very traceable. So when it comes to application on GC-HRMS, this is the first application. You can see this is based on the API, where the metformin is used, and in metformin we are targeted around 15 nitrosamine impurities. It's a very simple, you just have to extract and you can inject, and with the help of the characteristic of high resolution, you can get rid of all the interference and you can easily target up to nanogram level, up to 0.2 to 0.5 nanogram level, you can easily achieve, and the runtime for all 15 impurities is somewhere around 13 minutes. So this is the experimental data, and this is a simple sample preparation. Just take this metformin API, add your internal standard. Normally we are using NDMA D6 as internal standard. Vortex it, mix it, and then extract with the nitrosamine, back extract those impurities, and then after cleanup you can inject in a GC-HRMS. This is a full scan, exercise all the impurities at 50 nanogram per ml. You can see all impurities are well resolved and they are detected very well. And this is about the sample matrix. So you can see in TAC you are not able to see any of the impurities, but when you extract it at 5 ppm level, you can easily see these impurities. And when it goes to calibration, you can get all the 15 impurities calibration up to more than 0.99 R-square value. And only for representation, I have just shown the 4 calibration curves. Then for recoveries, you can see recovery limit is somewhere around 70 to 130 when you do the spike concentration. So we are achieving around more than 80% impurities for all the impurity levels. And for RSD, that is one of the more criteria. When you do the precision studies, you are getting less than 10% or 15% for all the impurities. And for precision study also, or long-term stability also, almost 2 weeks the same solution has been injected, and we are getting almost similar results for all impurities less than 3 ppm level. Now this is one more impurity for nitrosamine which we have done in formulation, because right now we are just talking about a metformin API, but what will happen when it comes to finished good. So this is a certain group of tablets have been taken and we have targeted somewhere around 18 nitrosamine, and we have taken the sample preparation path which is similar to the EP monograph, which is given in the EP monograph. So with the help of internal standard, we are extracting the extraction mixture, which is nothing but it's an NaOH solution, and we back extract with dichloropropane, and then after vortexing and filtering we are injecting in the system. The same 18 impurities we are done in less than 13 minutes, and you can see when you have a high resolution power on your instrument, you don't require a base-to-base separation. Like you can see 6, 7, 8 and 11, 10, they are more closely related. But when on the basis of accurate mass, you can extract and you can easily quantify this. This is a sample which we have extracted with the same thing. The upper one is the TIC, total ion chromatogram, which you can see very complex TIC, but when you extract, you can get the extracted ion chromatogram, where you can see almost all impurities are not detected. This is a peak shape which is just shown you at 1 nanogram per ml absolute concentration, where you can see all the peaks are well detected, and also peak shape is also really good. Then this is a sensitivity, precision, linearity study for all the 18 impurities, which is in tabular form, where you can see all impurities are detected up to 0.1 nanogram per ml, and correlation coefficient is also more than 0.999. So these things where we have done a sample preparation manually, we have done an extraction, then we have injected it. Now can we have an automated approach where instrument can do the sample preparation and it will inject and give you the results? So that is possible, and that is possible with the help of Tri plus RSS Smart, because in IIT SAIF also we have a Tri plus RSH, but with the help of upgradation to this system, we can easily do the automated way of sample preparation. So what we can get with the Tri plus RSS auto sampler? So we have a workflow flow where we can program in a such a way that sample can be extracted, cleaned up, and then injected by the system itself. And this will maximize your uptime, because nobody wants to be there to do the sample preparation, or nobody will be there to monitor the system. So it will automatically do the all activities. And this is a sampling technique which is available in Tri plus RSH. You can have different liquid injectors, then we have headspace, SPMP arrow, and as well as a dynamic headspace system also available in the system. So these are all models available, and as per our requirement, we can install in the existing RSS system. And there is one more tool which you can say it is a ATC, automatic tool chain. So benefit of automatic tool chain is that you don't have to switch it from tool from liquid to headspace or headspace to SPMP. You just have to give the command, system will automatically identify on which slot which tool is there, and accordingly it will change and it will do the injection. So what are the activities we can do with the automated? We can do the heating, mixing, we can do the vortexing, dilution, auto dilution. If you want to make a calibration curve, you just program in a such a way that it will do the all calibration level and it will inject it. You can do derivation, cooling, as well as a centrifugation. And these are the different tools actually look like auto diluter will be there, large solvent station, standard wash station, centrifuge, everything is available. So what we have done in automated approach, the same metformin where we are targeting 15 nitrosamine, we have converted this method into automated sample preparation. So for this we have used LS1 and LS3, two solvents module, because we need to change the syringe more frequently to introduce more volume, like 0.3 ml and 0.5 ml, 100 microliter. Then we have a large solvent wash station where we can wash the syringe in between. Then we have a GC-oil extraction station, and we have a dichloromethane as a solvent station. And we also perform this vortex and degassing. Workflow is like the same thing what we have seen in the metformin. We are adding 0.6 ml of water, in a vial containing 100 mg of metformin. We are vortexing it at 2000 rpm for 1 minute. Then we are adding 0.3 ml of dichloromethane. Again vortexing it so that it will mix and it will extract all the nitrosamine in dichloromethane. After that, we are centrifuging this vial at 3500 rpm for 2 minutes. So automatically all insoluble API and water will be separated out, and from that we are only taking this 100 microliter of dichloromethane and we are transferring to another vial, and so that we can directly inject. So here no manual error, you don't have to monitor the system, you just keep your sample and leave it to the system. System will do everything for you. And when you do it, we have measured accuracy and precision level. So we can see accuracy level is also in between 70 to 130, as well as the RSC is less than 15%. Even for long term extraction repeatability, it is in within the limit of 7%. So all those application notes are available. You can go to AppsLab at thermofisher.in. You can register, you can download. And even there is a possibility that you can also download the complete workflow. So if you are using the same software, just download workflow and open it in your software. You don't have to type anything. Instrument method, sequence, everything can be automatically created. Apart from this, there is a Thermo Fisher Highspot is also available, where you can get application note from all different chromatographic or different product line. Then the other major issue in pharma, which is the extractable and leachable. Right, sir? Anything I am missing from nitrosamine? Okay, no problem. So extractable leachable is nothing but it is the identification and quantification of the risk assessment potential toxic impurities which can transfer from your primary packaging, secondary packaging, tertiary packaging, as well as people are thinking about if I am using a label on my medicinal product on outer carton box, whether that label can also introduce some of the impurities in my product during my shelf life. So extractable normally it is done on a packaging material, and it is a pre-packaging studies, or at the time of development we have to do the study. If I am using a HDP bottle, so if my bottle, what are the potential impurities can generated from this packaging material, so that I can target in my leachable. Leachable is nothing but it's a study which is targeted to analyze all those extractable material in your finished product or your drug product. And you can see there is extractable, leachable, and there is also possibility that secondary leachables can also form, because see, when you are putting your formulation in different packaging material, there is a possibility that your formulation can interact with your packaging material and it can form some new compound which is not known to us, or we can say it is a completely non-targeted. So there are different regulatory bodies which have already given some guidelines to the industry, like ICH-Q3, which talks about the impurities, then FDA are also publishing. Then there are some industry groups like BPOG or LC, they are also publishing their guideline. Even the Pharmacopoeia USP has also published different chapters, 1663 on extractable, 1664 on leachable studies. And different extractable studies, you may require a different kind of multiple analytical techniques. That only GC-HRMS is not suitable, you can have different analytical techniques to be incorporated to cover all those extractable and leachable materials. There are some medical devices, ISO guidelines are also available. So day by day, these studies have been implemented or maybe carried out on each and every product in all pharma industry. So what are extractable leachables? So extractable leachables can come into any form. It can be a volatile impurity, it can be a semi-volatile impurity, it can be a non-volatile, or it may be a elemental impurity. So only one analytical technique will not give you the complete solution. So volatile impurities, normally as it's a volatile, so definitely we go with the GC-HRMS, GC-HRMS, or we can use a special sample introduction technique like thermal desorption, or maybe you can use headspace. And with the help of this, once you data acquire, we can compare with the library and we can identify those compounds. Semi-volatile, again it's semi-volatile, so GC-HRMS. With library matching, you can do it. Some of extent, we can also do this study on LC-HRMS. Non-volatile, obviously it means non-volatile means GC is useless there. The GC only works on the compounds which are volatile and thermally stable. So for this non-volatile, definitely we have to go with the complementary technique like LC-HRMS, and there are libraries available. And for elemental capabilities, we have to rely on all the ICP-MS or ICP-OS technique. So what we have in extractable leachable workflow, so we have everything is available to do the extractable leachable studies. Right from sample preparation, we can have a sample preparation like extraction and evaporation in the same phase. So you can do extraction and evaporation, and you can get the directly your sample collected in your sample vials. Then we have different vials, certified vials, columns, solvents are available. And when it comes to analysis and reporting, volatile, we can have a headspace with GC-MS. Semi-volatile, today we are talking about the GC orbit trap, so that also we can do it on either on GC-MS or GC-HRMS, but GC-MS will have some limitation, but HRMS will give you the complete idea about your extractable. Non-volatile, we have IC, LC, HRMS kind of the thing, and for ICP, trace elemental, you can do it with the ICP-MS. This is Extreva accelerated solvent extraction, so where you can keep your sample, and this is mainly used for solid and semi-solid. Like in Soxlate, we are using some solvent to extract the impurities. So same way here, we are doing the extraction at high temperature and high pressure, so that the same efficiency of extraction we can achieve in a shortest time. So normally Soxlate will take somewhere around 16 to 18 hours, or maybe sometimes 24 hours. The same sample we can do with high temperature, high pressure, we can do within half an hour. So now almost we are coming down from 16 to 18 hours to half an hour. And we can have a 4 channels, so 4 into 4, 16 samples can be extracted parallelly. And then we can send it to evaporation cell, where it will be getting evaporated and it will be pre-concentrated, and you can directly get it in your auto sampler vial, so that you can just have to put it in your system for analysis. Volatile, semi-volatile, we have 3 products in GC-MS. We have ISQ 7610, that is a single core machine. Then we have ESQ 9610, triple core machine, and then we have a Orbitrap Explorer system for GC. This slide we have already seen it during Sunil's presentation about the nominal mass and the accurate mass. So when you extract in full scan, and when you go for 184 nominal mass, you can see they are at unit resolution. That means resolution for all quadruple is 1. So I am targeting 78. So from 77.5 to 78.5, everything is 78 for this quadruple machine. So when you extract it, you can see very 38 peaks somewhere around you can get in 1 Dalton system, 1 Dalton extraction window. But when you do it the same thing at 5 ppm, you can get only 1 single peak. And this is the beauty of the HRMS. When you do it on HRMS, you can get more selectivity, specificity, as well as the sensitivity is also improved, because the data is acquired at very high speed, so you can at least get 26 points per peak. And generally for quantification, we expect at least more than 15 peaks should be good enough to give you a proper peak. That's the reason there are some limitations when you work in quad system like correlating compounds. When you have there is a correlation, you can see there is a complex spectra, and this complex spectra will not give you a proper identification. Same thing with unit mass, just we have seen when you have unit mass, you can't come to any final conclusion. and that time we can work on this HRMS system. So this is a normal workflow for unknown. We acquire data on EI. EI is a hard ionization, electron impact or electron ionization technique. When you bombard your system, your compounds get ionized. But while ionization, there is a possibility that there will be a fragmentation, and these fragments are unique for a particular compound. No two compounds will have the same fragmentation pattern unless and until they are isomers. And there are libraries available, so you can compare with the libraries and you can identify those compounds. But again, this identification you have to make it more confirmatory. You just switch it from EI to CI. When you have vacuum probe interlock, you don't have to break your vacuum. Within 2 minutes, you can switch your system from EI to CI. Acquire the data in CI. So here you can see, you can get a complete molecular RAM. So you can get the exact molecular weight, and based on the exact molecular weight and the isotopic pattern, you can confirm those compounds. So this way you can identify each and every compound with the help of system. And then this is the library matching where you can compare with the niche library, and there are also high resolution mass libraries available from the Thermo which are targeting ENL compound, then pesticide, then we have a contaminants library. So these are all libraries available. But the next point comes, why I want to do everything? Because see, if I want to sit there and I want to take each and every spectra in EI and CI, and I want to spend time for interpreting those things, maybe it will take at least a week, and that is also depend on how many peaks you are getting in your TIC. To avoid this thing, we also have a data processing software, especially in high resolution MOSFET, which we call as a compound discoverer. And currently the 3.3 is the latest version, and you don't have to do anything, you just have to extract the data and you have to put it in the compound discoverer. Compound discoverer will deconvolute those data. So there are different workflows are there. So you can see there is a EI workflow, there is a PCI workflow. So we just have to input the file, it will select the spectra, it will deconvolute it, and then with the help of library it will match it in EI. In CI, when you input the file, after deconvolution, it will go to the external database like ChemSpider, or maybe if you have added some high resolution library from the Thermo, so there it will search it and it will give you the identification of compound based on your accurate mass with the help of elemental composition. So this is the EI workflow, and this EI workflow works in this matter. First it deconvolutes the septa, then it will do the retention indexing, then do the library matching with the help of NIST or any high resolution library, and also it will give the peak grouping, so that with the help of ion ratio you can also confirm this thing. And your data looks like this. It will give you the peak matching, you can get the library spectra, and also you can get the all information about how much is the matching factor with the library. And in second phase, also second level, you can see the niche library structure to which compound it is matching along with the matching factor as well as the mass error. And also you can get the comparative spectra between the library spectra get on the instrument along with the library spectra. And also you can get this, like Dr. Kashtar mentioned about this fragmentation, phase fragmentation match. It can give you the how your molecules are fragmenting and what is the probable structure of your compound. And there are different statistical also analysis available in the same CD where you can get the different output chart like volcanograph or comparative or Whisker chart. So all things are you can do it. And for unknown identification, you can get the spectra at different electron energy, volt energy, because we can have a variable EV electron volt sources. So you can acquire the data at 70 electron volt, 12 electron volt, you can see the same fragment. And when you do it on PCA, you can see because of the soft annihilation, you can get the accurate mass, and with the help of elemental composition, you can identify those things. So all these application notes again available on the same HighSpot or the apps lab, so where you can also download and you can get more information up. And this is the complete workflow or complete product line available in the GC, right from the standalone GC, ISQ, TSQ, orbit of HRMS, and then electric magnetic spectrum GC-HRMS.